All right, welcome everyone. Today we're going to keep talking about polar curves. And where we left off from last time is we were seeing how to convert polar curves or polar equations back and forth between polar and Cartesian coordinates. And that's what we're going to do here. We're given this polar curve r equal to 3 cosine theta, and it's given in polar coordinates. We want to convert it into Cartesian coordinates, so our usual x's and y's. All right, so how we normally start these is we think about all of the different pieces, all the little different gadgets and x equations and y equations that we have to work with when we convert back and forth. So what do we know? We know x is equal to r cosine theta. That's one of our standard conversions. We know y is equal to r sine theta, another one of our equations. We know r squared is equal to x squared plus y squared, and then we know tangent theta is equal to y over x. So it helps to just kind of write down those four main equations that we use when we're converting back and forth. All right, so what are we going to do? Well, let's start with this equation. And we want to get rid of the thetas and the r's. We want to convert them in some way to x's and y's. So let's start with that cosine theta. Look at what we have, and we see that we have an equation here that involves cosine theta. So let's solve this equation for cosine theta. So we get cosine theta is equal to x over r, and that's what we're going to fill in. So instead of having, r equal to 3 cosine theta, let's change that cosine theta. So we're going to get r equal to 3, and then we're going to fill in that x over r in for cosine theta. All right, so this is looking pretty good. We have an x now, got rid of the theta. We still have some r's though that we need to get rid of. So let's consolidate them. Let's get all the r's onto one side. So multiply both sides of this equation by r. And that's going to give us r squared is equal to 3x. Okay. And if we look at this, r squared, yeah, we know what that is. It's x squared plus y squared. So let's fill that in. All right, and there we go. We have a nice Cartesian equation. X squared plus y squared is equal to 3x. So this is a Cartesian equation for this polar curve. Now, when we see x squared plus y squared, we might start thinking circle. And in this case, we can do a little bit more algebra here to really kind of make this a more recognizable format. So let's kind of review something really quick. What do we want to use for the radius? Normally we use r. Well, we'll use r. I mean, we're already using r, but we can use r again. So what is the formula for a circle centered at the point h comma k in Cartesian coordinates, h comma k, with radius r? So this r is just kind of, standard radius, not to be confused with the polar coordinates here. So, what's the general formula for a circle? And the general formula is x minus h, the x coordinate of our center point, squared, plus y minus k squared, y minus the y value of our center point squared, equal to r squared. So this is the kind of the standard formula for a circle that's centered at some point h comma k and has a radius of r. So when you start seeing this x squared plus y squared, we're thinking circles, and we want to get it more into this format. Not absolutely necessary, but it might be helpful in terms of picturing what this thing looks like. So what we're going to do is we're going to do a little bit more algebra with this. We're going to do completing the square. So we're going to move this 3x over with the x squared. Again, this step is not absolutely necessary. It's just going to help us kind of get a more of a feel, more of a picture for what this equation looks like. So we're going to move that x, or that 3x over, so it'll be x squared minus 3x. We'll put it next to all the x terms together. Leave a space. We're doing completing the square, so we're going to be filling some things in. And then we're going to have plus y squared, and then we've gotten everything off of the right side, so it'll be equal to 0. All right, so we kind of have this set up for completing the square. So now for completing the square, we take that number in front of the x and we divide it by 2. And just note here that the x, it's just an x squared. If there was a number in front, then we would have to factor. But it's already in a nice format here, so we can just divide this negative 3 by 2. So that's going to give us negative 3 halves. And then we square it. So we square this number. It's going to be positive 9 over 4 when we square it. We can't just add a number in. It's going to change the equation, so then we have to subtract it right out. So positive 9 over 4 minus 9 over 4. And with our usual completing the square trick, we look at those first 3 terms and kind of group them together, and those terms factor. And this number here tells us how they factor. So it factors into x minus 3 halves squared. And then we have plus y squared. And then this minus 9 over 4, let's move that to the other side. So it'll be 9 over 4 on the other side. So if we look at this alternative version for our Cartesian equation, what do we notice? Well, it matches up with this format here, and we can see what this thing is going to look like. So this is actually a circle centered at the point 3 halves, comma 0. So you can tell the x coordinate of the center point is 3 halves. And then the y coordinate is 0 because we have a y squared here. So that's like y minus 0. So like a y minus 0 here. So the y coordinate for our center point is 0. And then the number on the right-hand side, well, that's the radius squared. So the radius is actually 3 halves. So when we think about this polar curve, it's actually, if we think of it in Cartesian coordinates, it's actually a circle. Still going to be a circle, but now we can actually find, say, what the center point is, 3 halves, comma 0, and actually what the radius is of the circle, 3 halves. All right. Let's try graphing this one. So this is going to be a good introduction into how we actually graph polar curves. We kind of know what this one's going to look like already. We know it's a circle, we know the center point, we know the radius. But let's go through of how we actually, if we don't necessarily know how the graph is going to look, how would we actually sketch it? And the way we start this off is we first take this equation. Ultimately, what we want is we want to draw this thing in polar coordinates. So we have our polar grid down here. To help us with this, though, we're going to first start by thinking of this equation in regular rectangular or Cartesian coordinates. So that's where we're going to start. We're going to kind of think of this function as it is as in regular rectangular coordinates. So let's draw our normal rectangular grid here. And what we're doing is we're plotting r along the vertical axis and theta along the horizontal axis. And let's just draw what the graph of cosine looks like. So the graph of cosine, you should know this one. Make it little bit more symmetric. Well, that's even worse. Here we go. Well, all right. All right, one more time. We get at this. All right, better. And we know this is what the cosine curves look like. And it goes from 0. If it's just a regular cosine curve, it goes from 0 to 2 pi. And then it just kind of repeats from there. Now, what does this 3 in front do? Well, that constant multiple in front really just kind of stretches the cosine curve out. So it stretches cosine by a factor of 3. So normally cosine has its high point at 1 and it has its low point at -1. Now it's actually going to go up to 3 and down to -3. So it's just stretching it in both directions. So it's going to have its high and low points now at 3 and -3. All right, so we've drawn r equal to 3 cosine theta just to get an idea of what this thing looks like. And let's go through and think about, well, what are some of the values at the other important angles? So what are some of the important angles as we work our way around the polar grid? Well, we know 0 is 1. We know, pi over 6 is another one. Pi over 4 might be helpful, which is kind of like halfway between 0 and pi over 2. Maybe pi over 3 is good. Pi over 2 might be a helpful one. We just kind of work our way around the circle. So, 2 pi over 3, 5 pi over 6, and then pi. And then maybe we keep going from there. All right, so we look on our graph here. And cosine, what are some of the key things? Well, it hits its high point at 0 and then again at 2 pi. It hits its low point at pi, so halfway around there. Crosses the horizontal axis at pi over 2, and then again at 3 pi over 2. And then from there, everything is symmetric. So to kind of start drawing in our polar curve here, let's start at theta equals 0, and we're just going to work our way around the polar grid until we get to, as far as we need to go. So let's see what happens. Let's do a little table here. Keep track of the theta and r values. So when theta, and then we'll keep track of the r value that goes with it. So when theta is 0, we're on the positive x-axis here, the 0 ray. What is the r value for our curve? Well, we plug 0 into the function here. Look on our little sketch. We see the r value is 3. So when we draw in our curve, we're going to be at the point 3, 0. So 3 is the r value, 0 is the theta value, written in polar coordinates here. Okay. And then we're just going to imagine starting at 0, and we're just going to work our way around the polar grid here. We're going to go from 0 to pi over 2. All right, so let's see what happens as we go from 0 to pi over 2. Well, if we look at the Cartesian view, we see that the r values are going to shrink down to 0. So at pi over 2, if we plug pi over 2 into our curve here, what is the r value? Well, cosine of pi over 2 is 0. The r value is going to be 0. Or we can just see that from our sketch in the Cartesian view here. The r value is just going to be 0. So as we go around from 0 to pi over 2, we're just plotting points. And when we get to pi over 2, we're going to be at the origin there because the radius is 0. All right, so what do some of these points in between look like? Well, let's go to our important angles, plug them in. So maybe like a pi over 6. Let's try a pi over 6. What do we get when we plug pi over 6 into cosine? Well, that's square root 3 over 2. So the r value is going to be 3 times square root 3 over 2. What about pi over 3? So at pi over 3, what do we get? When we plug pi over 3 into cosine, we get 1/2. And so we're going to have 3/2 here for the radius. So when we plug pi over 3 into cosine, we get 1/2. 3 times 1/2 is 3/2. All right, so this one actually we can probably visualize right now. So let's look on this pi over 3 ray, and we want to go 1.5 units away from the origin. So we'd be around here. So we plot that point. 3 times square root 3 over 2, it's going to put us probably around, right around here. And what we're going to do is we're just going to draw a curve that's going to trace out those points. It's going to go through those points. So essentially, we're connecting the dots. Really, that's how we sketch things. You draw enough points, and then you just connect the dots. And we're just going to connect them with a curve. There we go. So we've gone through the first quadrant here, going from 0 to pi over 2, plotted a few points to help guide us, but we see, we started at this point here, and we shrunk down to the origin. All right, let's see what happens when we go from pi over 2 to pi. Well, the r values start off at 0, so we're going to start at the origin. So when we go from pi over 2 to pi, we're talking this realm over here. We're in the second quadrant. But what we see on our graph here is the r values are going to be negative. So when the r values are negative, normally if the r values are positive, we would be drawing things in the second quadrant. But because the r values are negative, we're going to go into the opposite. We're going to draw everything down here in the fourth quadrant. All right, so again, let's kind of work our way through going from pi over 2 to pi. So let's look at the important angles, and let's see where we end up. So maybe you do a little table here just to think of, what the different values are. So you look at your theta values, you look at your r value, the corresponding r values. So we know we're starting at pi over 2 and 0 for r. So let's see what happens when we get to pi. What happens when theta is pi? So if we look on our graph here, when we plug pi into the cosine function, we're going to get -1. So at pi, if we look at our sketch, we're going to be at -3. So the r value is -3. So what point would this be in polar coordinates? Well, normally if the radius is positive, when we're plotting something on the pi ray, it would be over here. But because the r value is negative, we're going to go on the opposite side. So we're going to count 3 units out on the opposite side. And what we see is that when we get to pi, we're actually back at this point here where we started. So when we get to pi, we're kind of back to where we started. So we had our starting point was 3, 0 in polar coordinates. And then when we keep going, we eventually get to this point -3, pi, but kind of geographically where we are, we're back to where we started. Even though it has a different polar representation, once we get to pi, we're back to where we started. And so to kind of see how the rest of the curve looks, we know we start going from pi over 2 to pi. We're going to start here. We're going to end up over here. To see how the rest of it looks, again, maybe just think of a few different r values, or look at the trig function at a few of these important trig values. So what, 2 pi over 3 is going to be, so 2 pi over 3 is going to be the same as pi over 3, except just negative. So negative 3/2. That's because cosine, it's the same values, but cosine becomes negative in the second quadrant there. And then what about for 5 pi over 6? What would be the r value? Well, it's going to be the same, except now it's just negative. So negative 3 square root 3 over 2. And a constant multiple, that 3 doesn't change the sign at all. All right, so let's think about plotting these points. So at 2 pi over 3, normally if the r value is positive, we would draw it on this portion of the ray. But because the r value is negative, we're going to go through the origin, and we're actually going to draw it down here in the fourth quadrant. So at 2 pi over 3, we're going to count out 1/2 unit. So we're going to get right here. And then this is going to look very similar. It's going to look like the mirror image, essentially. So when we get to 5 pi over 6, we see our point here. We're going to be about the same there. All right. And so we're starting at the origin, and we're going to work our way back to this point. And there we go. So essentially, we're just kind of filling in enough points until we get an idea of what the curve is doing. We're just plotting points and then connecting dots. All right, and what we see here is that once we get back to this point, if we kept sketching, we would just trace this circle out again. So going from pi to 3 pi over 2, normally when we would do that, that would be in the third quadrant. But if we look, going from pi to 3 pi over 2, the r values are negative. So instead of drawing things in the third quadrant, we're actually going to draw them in the first quadrant. So you can see we're just going to trace this over again. And then going from 3 pi over 2 to 2 pi, again, that would be kind of rotate. If we keep going around, that would be like drawing in the fourth quadrant. And here the r values are positive. So we're just going to trace those out again. So we actually, going from 0 to 2 pi, we actually go around the circle twice here. So that's important to note. If we kept drawing this, we would trace over that circle twice. And really how we know that is we actually sketched it out and saw that it only took us to pi before we got back to where we started. All right, let's try another one of these. So it just helps, just practice, try a few of these. But really it comes down to just plotting the points. Maybe you do a Cartesian view, take your curve, get a Cartesian view just to see what some of the important values are. If you need to, maybe do a table of some of the points. That can be helpful. And then finally, you do your polar view, where you actually draw in the curve. And this is where you might plot some of the points that you found on the table, or you're just identifying those points directly from the Cartesian view here. All right, so let's try another one. Let's look at the curve r equal to 1 plus cosine theta. So let's start this off. Ultimately, we want the polar view here. So we want to draw this in polar coordinates. So we have our polar grid. But to help us with this, let's draw in our Cartesian. Let's get our Cartesian view first of what this function looks like. So we're just going to have... We're going to plot r on the vertical axis. So we're just looking in regular rectangular coordinates. R is the vertical, theta is the horizontal. And let's draw in what this curve looks like. Let me extend this out a little further. All right, so what does this curve look like? And actually, we need to shift it down. I'm going to move the axes down a little bit because this 1 here, it's going to look like our regular cosine curve, but this 1 means it's just going to be shifted up 1 unit. So it's a positive 1, so it's going to be shifted up 1 unit. All right, so so what that means is normally cosine, the lowest it gets is -1. So when we look at this function, the lowest it could get is 0. And normally the highest cosine gets is 1, but the highest this function can get is 2. And then where it crosses this horizontal line r equals 1, well, that would be normally where cosine crosses the horizontal axis. So everything's just kind of shifted up by 1 unit. And so then we just draw in our regular cosine curve. So it starts up at its high point. Let's see if we can do this. Nope. So something like that. So there's our cosine curve, and we know it repeats from 0 to 2 pi. All right, so what are some of the other important values here? And I guess I didn't need to make the theta axis that big. What are some of the other important angles? Well, we know it hits its low point at pi, and then we know it crosses the horizontal axis at pi over 2 and 3 pi over 2. So you kind of start with these main angles, and then you fill in as needed. So a lot of times 0 pi over 2 pi, 3 pi over 2, 2 pi. You kind of start with those, and then you kind of work your way in to those smaller angles as needed. All right, so this is our regular cosine curve, just everything shifted up 1 unit. So let's see what we have to work with. So when theta is 0, the r value is 2. So let's start. Theta equals 0 is the kind of the positive x-axis. And we're going to start 2 units away from the origin. So we're going to start out here. So let's plot that point. And now we're going to imagine just kind of going counterclockwise around the origin. So we're going to get to pi over 2. Let's see what happens as we get to pi over 2. And when we get to pi over 2, let's look at our graph here, and we see that the r value is going to be 1. So we can draw on the pi over 2 ray, the r value is 1. So we're actually going to draw it right on that ray, and it's this point here. So again, 1 comma pi over 2 in polar coordinates, and here we've drawn 2 comma 0 in polar coordinates. And what happens is as we go from 0 to pi over 2, the radius value, the r value here, shrinks. So it starts at 2, starts at the high, and shrinks down to 1. So maybe to help us kind of fill in how things look, let's think about what happens at pi over 4. So this might be another one, another important angle that we consider. So what happens at theta equals pi over 4? So if we take pi over 4, plug it into our polar curve here, we get r is equal to 1 plus, and cosine of pi over 4 is square root 2 over 2. And this is roughly, 0.7. So we end up with about 1.7 as our r value, roughly. So let's think about where that would look on our polar grid. So we're going to be on the pi over 4 ray. The radius is positive, the r value is positive, and we're going to be about 1.7 units away from the origin. So we're going to be, roughly maybe somewhere around here. And what we're going to do is we're going to start at 0 at this point on the theta equals 0 ray, and we're just going to work our way over to this point counterclockwise. It's hard to do. Yeah, not too bad. There we go. So we've just worked our way counterclockwise, going from 0 to pi over 2. And you can see the r value here is decaying. Now what happens if we go from pi over 2 to pi? Well, the r value keeps shrinking until we get to pi, where the r value is actually 0. So at pi, normally we would draw something, if we're going to draw a point on the pi ray, positive r value would be over here, negative r value would be over here, but when r is 0, that means we're right at the origin. And so, again, we can see the r values are all positive. So that means we are going to be drawing, so as we go around from pi over 2 to pi, we are going to be drawing things in this second quadrant, but the r values are going to be shrinking. And so maybe to help us kind of see how they shrink, let's see what happens at this pi over 4 ray. So what happens at, well, 3 pi over 4. So that's where we are here, 3 pi over 4. What happens there? Well, we're going to end up with 1 minus. So the cosine value becomes negative, so we end up with 1 minus square root 2 over 2. This is about 0.3. So we're going to, on that 3 pi over 4 ray, we're going to go about 0.3 units away from the origin. So we're going to go maybe right around here. And so we're just going to draw our curve counterclockwise, but now our radius, our r value, is going to shrink down until we get to the origin. So we're going to end up like that. And then we just keep doing this. So we go from pi over 2 to 3 pi over 2. We see that we're going to start at the origin. We're just working our way counterclockwise again. Here's 3 pi over 2. And what happens as we go from pi to 3 pi over 2, the r values start increasing again, and we end with an r value of 1. So an r value of 1 on the 3 pi over 2 ray would put us here. And so we're just going to kind of do, everything's going to be very symmetric here. And then we keep going around. So we go from 3 pi over 2 to now we're back to theta equals 0, or another way to think of that is 2 pi. So we go around one more quarter turn here around the circle, going from 3 pi over 2 to 2 pi. And what we see is that we start with an r value of 1, we end with an r value of 2. So we're ending with an r value of 2 means we're back to where we started. So we're just filling in. And you can check, plug in a different pi, the different kind of pi over 4 related angle here, and you'd see you're right around 1.7 again. And so you just fill things in. You just keep going. And so this curve here, if we kept drawing this, we got to 2 pi, but if we kept going, what happens is then this curve is just going to repeat. We got to use it anyways. The extra axis there. So going from 2 pi to 4 pi, you're just going to trace this out again. And you can just keep doing this. You could keep rotating around counterclockwise around the origin, and you're just going to keep tracing over the same curve. So 0 to 2 pi in this case traces out the curve once. If we did 2 pi to 4 pi, it would trace it out again. All right, so just another example. It helps to practice these. Now this one, if you study acoustics and if you know microphones at all, you might recognize this kind of shape. This is called a cardioid. So you might recognize that for microphones. It's a pretty common type pattern, and it's related to polar coordinates. All right. Try another one of these, just for the practice. So we're going to do the graph of the polar curve r equal to sine of 2 theta. Let's draw this out. So we're going to start. We want ultimately the kind of the polar view here in polar coordinates. So we have our polar grid going on. But to help us with this, we want to first draw out we want to think about this function in regular rectangular Cartesian, Cartesian coordinates here. So we're going to do our Cartesian view, our rectangular view first for this. And not to be confused with x's and y's, we just want to think of this function where we're thinking of the output r as the vertical and the input theta as the horizontal. All right, so theta, r is the vertical. And let's draw this trig function. So sine we know looks like that. There's our sine function. Now we have this 2. What does that 2 do? Well, it kind of speeds up our trig function a bit. So normally sine repeats itself. It goes through one cycle from 0 to 2 pi. What this 2 does is it speeds it up. So now when we look at from 0 to 2 pi, there's actually going to be 2 copies of the sine function. So there's going to be 2 copies of sine from 0 to 2 pi. All right, so if we keep drawing this, we're just going to have a second copy. All right, so normally everything's getting sped up here. So normally it would do one full cycle in between 0 and 2 pi, but now it's going to do one full cycle in between 0 and pi. And then from pi to 2 pi, it's going to do another full cycle. So there's going to be 2 full kind of sine curves in here. And then normally it would cross the horizontal axis at pi, but now it's going to do that in half the time. So it's going to do that at pi over 2. And then at 3 pi over 2, it's going to do it again. And then normally at pi over 2, it hits its high point, but everything is kind of sped up now. So it's going to do it in quicker. It's going to do it in half the time. So it's going to do it in pi over 4 here. And then 3 pi over 4. It's going to hit its low point. And then it's going to repeat like this. So if you're not sure of some of these values here, these are the important angles. So just take pi over 2, plug it in. What do you get? You get sine of pi. Sine of pi is 0. So the r value here would be 0. What about pi over 4? Plug pi over 4 in. You get sine of 2 pi over 4, which is sine of pi over 2. That's 1. So we're just looking at, again, our important angles here, plugging them in, and just kind of getting a rough idea of what the Cartesian view of this function looks like. Sine hits its high point at 1, hits its low point at -1, and then kind of bounces back and forth in between there. All right, so let's start graphing this thing. And we're going to look on our view here. At 0, the radius is 0. The r value is 0. So when theta is 0, r is 0. So that means normally we would start on the theta equals 0 ray, but our radius is 0. So we're going to actually start at the origin. So there's our starting point. And what happens? So as we go from 0 to pi over 4, so where is the pi over 4 ray? Right here. There's our pi over 4 ray. So we're going counterclockwise around the origin from 0 to pi over 4. What's going to happen? Well, the r value here is going to increase until it gets to 1. So at pi over 4, we're going to be 1 unit away from the origin. So we're going to be right here. So this is 1 comma pi over 4. And so as we kind of move counterclockwise around the origin, the radius is going to be increasing. So we're going to start off close to the origin, and then we're going to expand out until we get to this point here. So the r value is increasing. Then we're just going to keep going around. We go from pi over 4 to pi over 2. All right, let's go to our graph here, see what happens when we go from pi over 4 to pi over 2. Well, the r value starts off at 1, and then it shrinks down to 0. So as we go counterclockwise, as we fill in what the graph is going to look like in here, the r values are positive, so we are actually going to draw them in this region. But we're going to start off at this point, and then it's going to shrink down to 0. So we're going counterclockwise. We're drawing this thing in counterclockwise, and we're back down to 0. All right, so there is one loop, one pedal, going from 0 to pi over 2. Now let's see what happens when we go from pi over 2 to 3 pi over 4. So that would be right in here. Here's 3 pi over 4. What happens when we want to kind of draw our curve that goes through this region? Well, when we look, the r values are negative. So we're not actually going to be drawing them in here. We're actually going to be drawing them down here. So the r values are negative here. So we're actually going to draw things in right down over here. So it helps to just kind of keep track of that. All right, so what happens at 3 pi over 4? Well, at 3 pi over 4, the r value is going to be negative 1. So normally, if the r value is positive, we would draw it on the 3 pi over 4 ray. But because it's negative, we're going to go opposite. So we're going to end up over here. So this is the point negative 1 comma 3 pi over 4. All right, so we're plotting that point. And what happens? So as we go from pi over 2 to 3 pi over 4, the r values are going to start off small negative, and we're going to work our way out to that point. So we're going to start off small negative, and then we're going to work our way out to that point. Okay. Keep going. Now we want to do 3 pi over 4 to pi. So that means we're over here. Here's the pi ray. And what happens at pi? Well, we see the r value is 0. So we're going to work our way back to the origin, it looks like. And the r values are negative. So normally, if the r values were positive, we'd draw our curve in this section here, this kind of angular wedge. But because the r values are negative, we're going to be drawing things down over here in the opposite wedge. All right, so what is our curve going to look like? Well, at 3 pi over 4, we know we're starting here. And then we're just going to work our way down, back down to the origin. So the r values are going to get closer to 0 again. And then you just keep doing this. So what else? What else we got? Well, we have a peak in here between pi and 3 pi over 2. Happens halfway in between. So what is that going to be? That's going to be 5 pi over 2. Or 5 pi over 4, rather. So you can just average those two endpoints together if you want. 5 pi over 4. So 5 pi over 4, also just figured it out by kind of seeing what was next up on our around the circle here. So 5 pi over 4 is the next one. So let's see what happens. We're going from pi to 5 pi over 4. So now our R values are positive. So where we draw our curve is actually going to, fall, where it's supposed to. The R values are positive, so we're going to draw things where we actually are. And what happens? So at pi, we know we're starting at the origin because the radius, the R value is 0. And the R values are going to increase from there until we get to 1. So we're going to work our way to this point here. And this is the point 1 comma 5 pi over 4. So we know the R values are positive. We're drawing it in the correct wedge here. And then from 5 pi over 4 to 3 pi over 2, we're just keep going around the circle. Here's 3 pi over 2. Just working our way around. So we're going to start off at our high point, and then we're going to work our way back to the origin. And the R values are positive. So what does that mean? Well, when the R values are positive, you're going to be drawing in the actual wedge there. So the R values are positive, but they're just getting down to 0. So eventually when we get to 3 pi over 2, we're going to be back to the origin. So when you're drawing these in, think of we're going from 5 pi over 4 to 3 pi over 2. If our R value, we're looking at our graph here, and what we're seeing is that the R values are decreasing until we get down to 0. If, say, the R values were staying constant, well, then we would have, we would just stay constant as we go through that section, go through that wedge. But instead, what we're seeing is that the R values are going to decrease. So you have really 3 options. What are your R values going to do? Stay the same? Are they going to increase, so you're going to move away from the origin? Or are they going to decrease so that you're moving closer to the origin? So when we do this, if it were to stay constant, we would just go along the circle then. But our R values are actually decreasing, so we're going to actually shrink back down to the origin. All right, so we got a little bit more to go. Let's keep going around the circle. So where's next up on our list here of places to go? Well, we're going to 7 pi over 4. So here we have our 7 pi over 4 ray. It's a really nice place. So we're going from 3 pi over 2 to 7 pi over 4. We're just going around the circle. Graphically, we look at our Cartesian view here just to kind of get a feel for, for what our values are going to be. So now we see that we're starting, when we go from 3 pi over 2 to 7 pi over 4, we're starting at the origin, and the R values become negative. And then we end up with a -1 here when we get to 7 pi over 4. So normally if we're drawing things in 7 pi over 4, if the R value is positive, we would just draw it on this half. But because the R value is going to be negative, we're actually going to be reflected through the origin. So we know we're going to end up at this point over here. So this point is -1 comma 7 pi over 4. All right, so we're drawing in, we're interested in drawing the sketch in for this region, but the R values are negative. So what we're going to do is we're actually going to draw them in right over here in this wedge. So we're starting off close to the origin. We're starting at the origin, and then the R values are we're gonna work our way away from the origin. So starting, that's no good. We're going to work our way out to that point. And then finally, going from 7 pi over 4 to 2 pi, we're working our way back. So this is, now we're at 2 pi here. And what happens? The R values are negative. we're starting at that furthest point away, and we're working our way back to the origin. We're working our way back to an r value of 0. And let's see how this is going to look. So normally we would be drawing things in this wedge, but because the r value is negative, we're going to draw them in the opposite wedge. So we're going to be drawing them over here. All right, so we're going to start at, we know we're starting at this point here, and we're just going to work our way back to the origin. There we go. And then from there, it's going to repeat. So if you kept doing, if you did 2 pi to 4 pi, you're just going to trace this whole thing out again. And so just for the fun of it, we're not going to do it again. I was going to say, let's do it again. These take some time. But once you get the hang of it, they're not too bad. But let's just see what this would look like if we traced over this. Let's kind of replay this all in a fast motion. So we started at the origin, and then we work our way around. And then we're back. So you get these kind of, polar curves are fun. You get these really cool shapes that you wouldn't normally be able to get if you were kind of stuck in Cartesian coordinates. You get these really kind of interesting kind of shapes. All right, so this is just some practice graphing or sketching the graph of polar curves. Now, what we're going to see in the next couple lessons is we want to be able to calculate the area. So, for instance, calculate the area of inside this polar curve. Very, very reasonable thing to want to do. We're going to see how to do that. Also, we want to be able to calculate the length. So it would be like the length of this petal here. That's another thing we're going to be interested in doing. So we're going to see how to do both of those in the upcoming lessons. All right, so this one was just practice on, first working with these polar curves, sketching them, being able to kind of picture what they look like. And next we're going to see, how can we actually do some calculus with them. All right, so we'll see you then. Bye-bye.